In this video, we'll examine a 3-degree of freedom system, but this method employed should be general enough to be able to be used for any multiple degree of freedom system, even larger than 3. As we get to more complicated problems, it's very difficult to find any sort of analytical solution in closed form. So the idea here is to set up the equations of motion and then to prepare them for solution by direct time integration. And in the following video, I'll show you how to code that up and use a computer to solve this. So the starting point is we have 3 masses in this system, mass 1, 2, and 3 as labeled. These masses have coordinate systems associated with them, x1, x2, and x3 respectively. And the masses are 2m, m, and m. These masses are linked as shown by springs of stiffness k. It can be assumed that each of these 3 springs has the same stiffness constant. And it's configured as shown, where the first mass is tethered to a wall and the other 2 masses are connected to mass 1. And we'll assume that all motion exists only in the vertical direction. I've included Lagrange's equations. We're going to use Lagrange's equations to set up the equations of motion. And in order to get started, we need to find expressions for T, the kinetic energy, and V, the potential energy. I've recognized in the case of equation 2 that the kinetic energy in this problem is a function of the velocities only, and the potential energies are a function of the displacements only, which allows us to rewrite Lagrange's equations in this form, seen in equation 3. We begin by writing an expression for the kinetic energy of the system, and the kinetic energy, which we'll call T, is simply the sum of the kinetic energies of each of the 3 masses. So mass 1, it's a half times the mass, which is a half times 2m, gives us m, times the velocity squared. So that would be x1 dot squared. Plus, for the second mass, 1/2 m2 x2 dot squared. And for the third mass, 1/2 m3 x3 dot squared. Call that equation 4. And for the potential energy, which we call V, that is equal to, when mass 1 deflects by an amount x, you get 1/2 times k times x1 squared. If we look at the second spring, which I'm calling that one that I circled, we get a contribution of 1/2 times k times the displacement of that spring squared, which is x2 minus x1 squared, quantity squared, and then 1/2 k times x3 minus x1, quantity squared. We'll call that number 5. Okay, so substituting 4 and 5 into 3, 4 and 5 into 3, and then differentiating with respect to each one of the generalized coordinates, we get the 3 equations of motion. So in the case of the x1 coordinate, we find that it's only this term of the kinetic energy that contributes, so it's m, or 2m I should say, x1 double dot, and then from the potential energy plus k x1 minus k x2 minus x1, and then minus k x3 minus x1, and that is equal to 0. That's your first equation of motion. We'll call that, we're going to call that number 6. For the x2 coordinate, we end up with mx2 double dot plus k into x2 minus x1, and that is equal to the force here, the generalized force, which in this case is equal to F of t. This is equation 7. And in the case of x3, we get something similar. mx3 double dot plus k into x3 minus x1. In this case, it's equal to 0. That would be equation 8. All right, so I'm going to rewrite this in matrix notation because it allows me to be more compact. Let me write it first and then put the brackets. 2m, 0, 0, 0m, 0, 0, 0m times x1 double dot, x2 double dot, and x3 double dot. That is a vector. And then we group the stiffness matrix. We end up with 3k minus k again, minus k, k, and 0, and then minus k, 0, and k. That is multiplied by the coordinates x1, x2, and x3, which is also a vector. And this is equal to, let me try and squeeze it in, 0, f of t, and 0. This we'll call equation 9. Let's turn the page. So I've gone ahead and I've recopied this equation here. This is equation 9. And the idea is, and following on from a previous video, so I won't spend too much time explaining it. Here is a link to the video you can click on if you need it. But the idea is we need to put this into a form known as state space form. And the idea is that instead of it being a second order derivative, we would like it to be a first order derivative or a first order differential equation, because then we can integrate it directly. So state space form, involves a change of variable, and I'm going to change color for this, keep it a bit clearer. The idea is we're going to come up with a new variable called y, or a vector called y, and y is equal to x dot and x. So we take the x dot vector and the x vector and we stack it into one vector. I'm putting a dotted line here just to try to keep it separate. And the idea is where we originally had a vector that was an n by 1, this vector is now going to be 2n by 1. And whereas our mass and stiffness matrices were n by n, you'll now see that our new matrices will be 2n by 2n. So the idea is we're going to reduce the order of the derivative in the equation from second to first order. And the price that we pay for that is we end up with a system that is 2n in size instead of n. So we've got twice as many equations to solve, but they're much easier to solve and can be readily computed by a computer. So what follows on from this, we'll call this number 10, is that if I take the derivative of y dot, I end up with x double dot at the top and x dot below. Call that 11. Okay. And another thing to recognize, we'll take the original equation as we have it. Let me just rewrite it in the form. So equation 9 can be rewritten obviously in its usual form, m x vector double dot plus k x vector is equal to, we'll just call it lowercase f, vector f. We'll call that number 12. Okay. And let me, I think, just write it out and then explain what I've done will become clear. In state space form, this will look like m 0, 0, and I, where I is the identity matrix, and the 0 matrix is a matrix full of zeros. That is x double dot times x dot plus 0 k minus I 0. And then this is x dot, this is x, and that's equal to, we've got this vector up top f, and at the bottom 0, but it's a 0 vector. We'll call this 13. Alright, so what have I done? Let me just put some dotted lines in here to kind of show the partitions. And let's just look at the top half, the equation above the dotted line. What that says is that m times x double dot plus k times x is equal to f. Well, that's exactly what we have in number 9 above. So we haven't changed anything there. What we've added to the mix is at the bottom we've said that I times x dot, which is x dot, minus I times x dot, if you multiply those through, is equal to 0. So what we've said is x dot minus x dot is equal to 0, which seems like kind of a meaningless equation, but it's otherwise known as a constraint equation, and what that does in terms of the mathematics is it keeps everything consistent. But what I've been able to do now is, in effect, I've been able to write it in this form where we can call this first matrix A, we can call this vector y dot, excuse me, as we defined it, plus another matrix B times y is equal to, and I'll call this capital F. And we'll call this number 14. So I've converted equation 9, which is a second order differential equation, into equation 14, which is a first order differential equation. And I guess we should make the point that each one of these matrices is now 2n by 2n, because each one of these submatrices is n by n, n by n, n by n, n by n. This vector is now 2n by 1 because we took the original n by 1. This one here is also n by 1, the 0 vector. And you kind of get the idea. And we'll see in a second why it's so much better in this form, because we can implement it into a computer. Well, I can rewrite 14 as a difference equation, where it says that a times y, the vector y at time t plus 1, minus the vector y at time t, divided by delta t, plus b times y at t is equal to f at time t. Does that look like anything yet? Let's rewrite it in the following form. Y, which is the state vector at time t plus 1, can be calculated, if I rewrite this, by taking y at time t and adding to that delta t times the inverse of the A matrix. This is just some matrix algebra. Okay, maybe you want to do it on the back of an envelope to check it. Times f at time t minus by at time t. We'll call this equation 15. So the idea is, if I know the state vector y at any given time t, I can find it at the next time step t by 1 by doing what? By adding to it the difference between the force, and this is kind of your ma term, your kx term, right? All I've done is I've taken this here and moved it to the other side of the equation, subtracted it. And then you don't really divide by the matrix A because it's a matrix. What we do is we pre-multiply by A inverse. When I pre-multiply by this by A inverse, I get the identity matrix. It kind of cancels. And on this side, I get I then bring the time over to the other side and multiply. And then I add yt. So the idea is that initially, at time equals 0, we are given the state, typically. We know y at 0 is equal to, well, in this case we'll call it 0, but in general we can call it some known vector y of 0. Okay? And this, a reminder, would be a 6 by 1 vector. It's 2n by 1. Right, so we're going to make, let's go through the method, and then we're going to implement it in the following video in code. But the idea is that if we know the matrix or the vector y, the state vector at time equals 0, which we can assume is a given, for now we'll just assume it's 0, y 0 equals 0, it's a 0 vector, 2n by 1. Then we know everything else, and by picking an appropriate time step delta t, we can advance this solution step by step and calculate the state at the next step. Once we have the state at the next step, that becomes y of t, and we can plug this all in and we can advance it to the following time step after that. So I'd say for the purpose of solving this, let me just give you a few details. Given, we'll assume the following. That the forcing function f of t is sinusoidal, it's harmonic, so it would be something of the form f naught times sine omega t. We'll assume that f0 or f naught is equal to 5 newtons, keep it in SI units, it's a force. Omega will be 10 radians per second. We'll assume that each of the masses, or that m is 1 kilogram, so the big mass would be 2m, 2 kilograms. And then k, which is constant for all 3 springs, would be 1,000 newtons per meter. Alright, in the next video I'll show you how to solve it by computer, but in the meantime I hope you find this useful. If you have, please go ahead and give it a thumbs up. It will mean that other people get to see it. And thanks for watching. We'll catch up with you in the next video.